Good morning, everyone. My name is Vignesh Gopakumar. I done a couple of roles, and they're all part of like the logos over there. So I'm a senior AI research scientist at the UK Atomic Energy Authority. We're a government-run fusion research lab. I'm also a PhD student at UCL, and I have the role as a chief data officer at SimView, which is a simulation management tool company that's sort of being built in Oxford. So I'm going to talk about this recent work that we've sort of published, which challenges specifically around the idea of surrogate modeling and how we can make it a lot more useful in the context of engineering. And before I get into like the what and like what the actual mechanisms are, I want to take a step back and like really explain the why. So the why, the big challenge of the why that we started discussing in our lab is why do we need surrogate models? And looking at this particular engineering S-curve that we love to sort of pull up is that fusion as an industry is at the lower end of it. Where if you were to think about it, SpaceX is at the top end. I know it's a very touchy topic to talk about SpaceX and Elon Musk today, but sadly the slide was made last week. But we cannot afford to like build a lot of reactors and burn them up and break them and explore our engineering iterative process, and that's it. We have to look at other options just because it's just not practically feasible for us. So we've been heavily investing in exascale computing, scaling up our simulations, looking at how we can design and understand the plasma by building really good simulators in that context. But there's still a challenge that comes along with simulations, is that they are very complex. There's a significant amount of latency. Some of our full-scale 3D simulations that we end up doing, they actually end up taking about weeks, if not months. And that's not a good like process that we can scale up either. So how do we sort of like come up with these challenges is what drew us towards like surrogate modeling. Can we get modern surrogate models such as neural networks to maybe approximate the solutions a lot faster? So this is sort of the general structure of a surrogate model ecosystem, the way we've been seeing it. So very typical to a numerical sort of like physics solver. We feed it with all of the information required for a well-defined PDE. So your initial conditions, your boundary conditions, the PDE coefficients, its geometry, its architecture is all fed into numerical solvers to generate data, which is sort of used to build a surrogate model. The idea is that can we approximate a solution at a significant speed up as compared to a numerical solver, even if it's only an approximation. But the big challenge that we face is compared to numerical solvers where, most often it doesn't converge, it, explodes. We're aware that this is not a true good solution. But in the case of a surrogate model, as you've mostly seen with, neural network, other kinds of neural networks such as like an LLM, you're bound to get an answer. You will be given some sort of a solution, whether it's wrong or right is never really evaluated. So this is kind of the focus of this talk, is this gray shaded area where we want to talk about how do we sort of like look at uncertainty quantification from the perspective of these neural PDE models, neural ODE models, these sort of surrogate models which are being deployed in science and engineering. So now we got to think about of course, this is a topic which has been discussed for decades, if not longer. What is the sort of issue that we have with our current UQ methods? So our deep sort of neural networks and every kind of neural operator methods that we've been looking at, they are generally deterministic in its nature. There's obviously a lot of ways to make it slightly Bayesian in some sense, use some sort of like variational inference schemes. But then again, they fail to scale to high dimensions. They require extensive sampling, making it kind of expensive to explore. And they often fail to capture out of distribution. So let me explain like what this sort of looks like in an actual neural PDE case setting. So the issue is that we don't get validity or any guarantee over our error bars itself. So in this case, we have sort of a very simple wave equation that we're going to start with. So we have a wave equation solution at the top. We have a neural network that's trained to predict the wave solution. Very badly, I must say. And this neural network is fitted with, it's got Monte Carlo dropout attached to it, so it's doing some sort of variational inference to estimate an uncertainty error bar. As you can see, it's really not capturing anything in terms of the error. So without having much context as to what the solution needs to look like, if I was just given this pre-trained surrogate model and deployed, I will have no idea like if this error even makes sense whatsoever. So we started playing around with this idea like, okay, now how do we sort of calibrate this? Can we look at ways to maybe make sure that we have cheap estimates of error, but can we improve the quality of that error and then build up from there? So this is sort of the work that we did last year, which was to sort of take a stab at using conformal prediction to get us more calibrated error bars. So it's a very straightforward approach that we've taken. So it is a cell-wise marginal conformal prediction. So with each cell of our spatiotemporal output, as long as the tensor is not changed around, it's left immutable, we can obtain like calibrated error bars over the entire prediction set. Which works. You can see that the error is sort of like capturing what is being missed by the neural network. It sort of like scales to infinite dimensions. It doesn't care about what your neural network model is. It's still giving you like valid coverage guarantees. But there's that one key word which keeps coming back to bite us, is the statistically valid part of it. The big challenge is that we require sufficient calibration data to sort of we get these calibrated error bars, and we need that data for each prediction regime that we want to like really explore and understand and study, which became a big problem because, again, like I said, these simulations aren't cheap. We can't afford to build 100 and 1,000 for each of these case settings. This is sort of like the full premise for what I want to talk about is how do we sort of solve this problem? We want good error bars. We want to understand how good our models are as we deploy them downstream, but we can't afford to generate expensive calibration data either. So we started taking a step back. Okay, why do we need calibration data in this context to begin with? And it mainly comes from the fact that it is in that entire calibration process, right? It's the idea of a non-conformity score. You need some measure of how bad your model is, how bad it's sort of like fitting to your ground reality or the truth that you're interested in. So if that's the case, if all we care for is this sense of error, why don't we take like another perspective on this altogether? So we took a step back. This is very much what physicists end up doing, is we take a step back to like, how do we even solve these equations in the first place when we don't know the true solution? So all of these solvers are effectively formulated as a linear system of equations. We have this, it takes this form of ax equals b, and we try to minimize the residual that sort of evolves from it. So if you already have an understanding of like how bad the solution looks, or how bad like a particular prediction/solution looks for the ground reality, why don't we use sort of this structure to maybe inform us and formulate the non-conformity scores? So at the bottom we have like for well-defined PD, it sort of takes that residual approach. So if we're trying to predict PDs and we have a sort of solution that is attempting to fit that, why don't we try and evaluate this and see if this could be used as non-conformity score? This is sort of our the research direction that we took. So to give you an understanding of how this looks for the wave equation that we've been looking at, this is the simple 2D wave equation that we have at hand. U is the field that's sort of evolving, and C is the wave velocity that we're interested in modeling. So residual takes a very simple approach. All we have to do is just basically take its canonical form, make sure everything's put on the right-hand side, and see if that goes to 0 or not. If it goes to 0, yep, we've got a true solution. It fits as good as our understanding of the PDE is. Now, the big challenge over here is obviously that we are going to need a lot of gradients, but that is the big advantage of neural networks, is that everything exists on a computational graph. Gradients are cheap. We can evaluate them as many times as we kind of want. So that problems have kind of been baked into these neural PDE models that we can estimate like very cheap and good gradients. So how does this like fit into a conformal prediction framework? So this is sort of like our standard inductive conformal prediction setting, where we're using our non-conformity score as just an absolute error residual. So we have the prediction and a target, a labeled data, as to which is how the model should perform. So we basically estimate like an absolute error across it. Once we can estimate that non-conformity score, we can estimate the necessary quantiles, which will give us the valid error bars in that prediction regime. So within the residual domain, what we've sort of taken is there's a slightly different approach that comes in. So we don't need any calibration data anymore. That's got to do with the fact that now our true target solution is actually 0, because if your neural PD is that good, if your prediction for that particular regime is really good enough, then when you evaluate the residual over it, it should ideally go to 0. So we've taken away this idea of requiring a target, and we are able to get error bars just based on the fact that on the estimation of the physics residual error, which gives you these error bars which are completely independent of your prediction data. This is it's also kind of a different approach. Intuitively, it creates a different approach to like conformal prediction, because in standard conformal prediction, what you're obtaining is that these error bars, your true solutions are valid to be fitting within that error bars, but we're also adding this hypothetical, this statement that it's not just a true solution. Now we're saying is that our prediction domain will fit in the error bars obtained in the residual space. Now there's a key thing over here. We're not obtaining error bars in the actual physical space, we're obtaining it in the residual space. And I'll get to that in a bit and why that's actually okay for us. So this is the sort of full conformal prediction framework with physics residual errors. So you have a set of initial conditions or a PDE parameters that you're interested in modeling for a case. It's passed through a neural PDE, which gives you a prediction, which is probably bad. And then you estimate the physics residual error, auto-diff your way entire across it, use finite difference, any of like gradient estimation. Once you have the physics residuals, you can use our conformal prediction framework, which works both in the marginal and the joint. I'll talk about the joint in a bit, to give you error bars across that residual space. Now, why is the residual space okay with us? Because when we're actually evaluating this measure of physics residuals, we're actually understanding how well is the solution fitting to a conservation of mass. How well is it sort of obeying the momentum? And it's a very relevant metric to see like, oh, this is actually very unphysical and this is not a solution or a prediction that we should trust, and we sort of should go back to the actual numerical solver in the entire formulation of it. So we can get both a marginal and a joint coverage. So the marginal coverage is sort of what I described. We're getting it at each particular cell in your prediction sets, each particular point in your spatiotemporal domain, which is kind of, it's good because it helps us identify regions within that domain which the predictions are getting wrong. It could be the fact that there's some boundary interactions coming along that side, or maybe some vortices are forming, turbulences are arising in a certain region. It sort of helps us understand that. But we also want to have like a joint formulation. I think this has been discussed quite a lot over the past week, where all we take is that once we have this residual error, we estimate the supremum over it modulated by this particular function to get a joint error bar over it. So this is not a cell-wise, this is across the entire spatiotemporal domain of interest. So we're getting an error bar which says that out of 1,000 predictions you've got, there's like 50% fall within this error bar, which is a really good metric for us to do rejection sampling, which has been helpful to us to understand which parameters of your domain space are where the surrogate model is good, and which parameters of your domain space we should just sort of dump and maybe go back to like the actual numerical solver. So now this in practice for the wave equation sort of takes this approach, that this is sort of the prediction that we have up top. It looks pretty good. It's, to the naked eye, it seems like this is exactly how the solution would look like. The physics residual error evaluated over that is given on as in the second image. You can see that it's a bit noisy, and neural networks are terribly noisy. We can't get like a very clean solution. And we have the error bars that arise from the marginal conformal prediction next, and then the joint conformal prediction next. What you'll notice is that the joint conformal prediction is obviously order of magnitude higher because we're looking at bounds across the entire spatiotemporal domain, not cell-wise. So it gives like a really, and taking the supremum gives you like a really big error bar as well. But now we have a method of performing uncertainty quantification, which is guaranteed in its residual space, which is model agnostic. So this is fully on the output of the data. It doesn't matter whether it's an FNO or a physics-informed neural network or a transformer. It could be from ChatGPT, it doesn't matter, as long as you've got the solution space. You don't need any modifications done to the model. It doesn't require any sampling. It's completely data-free. All you need to do is like formulate this physics residual error in any way that you kind of want, and it's physics-informed because we're actually measuring how much the model is deviating from our understanding of the ground truth and reality as well. So let me walk you through like a very simple example to sort of see how the error bars look in practice. So this is a very simple 1D advection equation. We have a neural network. I think it was a Fourier neural operator that was trained to sort of model it. It does a decent job of understanding like the peaks, but it's still kind of noisy at the bottom. But then we can apply these error bars in the residual space and still sort of understand the bounds for it, right? So in the marginal, we can see like, okay, I think this is sort of built for like 80% coverage. So we can see certain areas where it's not fulfilling the coverage guarantees. And these are areas where you probably want to take a look at with the numerical solver. You want to understand why these areas like are the models performing fairly poorly. And with a joint CP, it's now just a good space to understand like which are the parameter regimes where this model is doing fairly poorly. So at that point, you could go back to your numerical solver, do a full active learning loop, and then improve the quality of a neural PDE solver that comes in. And that's something we're actively working on and been like getting good results to see how do we improve the quality of these neural PDE solvers and like by just implementing an active learning loop. But this also gives us like a good measure of like model quality as well. So here we have two neural network surrogate models built for the advection equation, where one's kind of good, one's kind of like actually doing a fairly good job of modeling it, and the other is terrible. So it's just trained without not sufficient data, maybe not a good choice of hyperparameters, whatever reasons it might be. It's just a terribly bad model. But when we take our PRE-CP framework over it. The quality of the error bars sort of indicate the quality of the model as well. And it's why that's interesting is the PRE itself is a good measure. But there's challenges of it. The PRE could be the fact that you've used a coarse approximator, which is mostly the case because you don't want it to be expensive. But this also gives you a statistical understanding of the performance across an entire regime rather than just one particular sort of prediction. So it gives you an understanding of how well does this particular circuit model behave when your diffusion coefficient is like this, or where in this interested regime of initial conditions and whatnot. It gives you a full solid measure to sort of see. And these are again like fully bounded, sort of valid within that entire regime that we are looking at. Now, this is all been toy examples. I'll give you quickly walk you through one of our really challenging examples in this where this model has been like really come in handy. So I'm going to give you a quick 1-minute crash course in tokamak design. So tokamak is a magnetic confinement fusion reactor. This is the most sought after design in the world. This is what we practice a lot back in Oxford. We have, well, one device which is actively functioning. We're doing a lot of tests on it. We have 2 more in the plans and under construction. So the key thing you have to understand is that there's very hot plasma. It's 100 million degrees in the middle. And it needs to be 4,000 by the time it reaches a wall, which is a meter away. So we've used very strong magnets to sort of contain it. And these magnets are what I'm going to talk about. So this magnets that you see in the blue and the silver, these are high temperature superconductor magnets which have to sort of like confine the plasma within that space. And this determines a lot about what we call a plasma equilibrium, how stable this plasma could be, and its position and the sort of like magnetic values. So if you take that particular silver magnet that we have, which we call the colloidal magnetic fields, designing of the placement of that is an open problem. We still have an understanding, but as we design like larger scale devices, we still don't know how to, what the most optimum scenario would be. So on the right, we have it's a cross-section plot of that. And this is what a magnetic equilibrium looks like. So these contour lines are magnetic, where the magnetic field exists and the plasma revolves around. What we want to know is how these particular colloidal coil positions, by changing the position of it, how much does it affect the quality of this sort of magnetic equilibrium that comes along? And it's a very open problem that we kind of face as we look into design. So the objective that we have is what is the optimum position for this particular coil as it needs to be to get a certain good, what we call a good equilibrium, which is confined, which is makes the magnets also kind of cheaper because it's very expensive. And the plasma lasts a lot longer, so we can like sustain a fusion reaction. So there is this big equation called the Grashof-Nov equation that solves for it. We have numerical solvers. We've built a range of numerical solvers, but then again, they are expensive. They take, some of it might take about certain minutes to hours to sort of run. But the problem is to explore this design space properly, we'll have to go through a million iterations. So it doesn't really scale that well. So we built a surrogate model. It was a conditional autoencoder of sorts, which can sort of predict how this would evolve for certain different like plasma colloidal field positions. So as you change the magnetic field positions, how does it sort of like change with the prediction? And now, applying our framework over, we can get upper and lower bars. So now, again, the question of trust comes in, right? You have a surrogate model which gives you 1 million evolutions in a matter of like minutes, which is great. But now how do we evaluate how good the surrogate model is in that particular regime of plasma operation that we kind of want? So this has actually been helpful for us to determine the quality of the surrogate and like knowing when to actually trust a numerical solver and then come back to the surrogate. So it's been a full iterative loop interacting with the numerical solver and the surrogate model with this framework right in the middle, which allows us to like talk and communicate. So to sort of conclude, with this method, we have a valid sort of guaranteed bounds over the conservative space of these neural PD solvers. It is data-free, it's physics-informed, model-agnostic UQ method. We've got 2 approaches we've played around with. So marginal CP allows us to identify regions in your domain which are bad. Joint CP allows us to sort of understand predictions that are bad. And lastly, this is not really limited to like PDs, even though that we work a lot with PDs, and this is sort of my thesis is looking at neural PDs. This can be extended to any of these models which has a standard canonical form. So it could be applied to ODEs as well as like anything with algebraic constraints as well. So this has been just accepted at ICML, and yeah, been preparing a paper for that in the past well. Thank you.
Questions, Vignesh? Please.
Maybe I missed, but
in the case of dynamical systems, the property of exchangeability that is crucial for conformal prediction is not so obviously satisfied. So, yeah.
So I guess it's the formulation of the PRE that it needs to be, you can change around. So it's as long as the interested domain that you're looking at, and you've sampled parameters. When I say parameters here, it's a parameterized PDE setting, so initial conditions, boundaries, or PDE coefficients. As long as you've sampled that in your PRE evaluation, we sort of like meet exchangeability at that point. So you create like so it's easy to create, because we have data free, right? It's easy to create a large prediction set based on that parameter. So it's kind of like non-consequential in that context.
I was going to ask, in your PDE examples, you often have free parameters, like your advection rate.
Yes.
How are they dealt with in the optimization?
So we have to normalize them or make the equations dimensionless, because otherwise the PRE the value itself would change a lot.
Yeah.
So that's we haven't found, I mean, I think it's also like an open problem with numerical modeling is that there's no standard way to normalize them or how it goes along. So we've done a problem by problem approach, and especially when we were doing active learning, we just need like a relative scale to compare. That actually has come up quite a bit. So it's a lot of normalization that we end up doing, or if we can, we take a dimensionless sort of form. So instead of viscosity, we will formulate into a Reynolds number and then sort of like keep it going.
Great, thank you. Oh, sorry, I'm going to go on, we've got time. Yeah, please.
So thank you for the talk. I was wondering, so you mentioned at the beginning, so you work in the spatial temporal domain, like pixel by pixel.
Yes.
Is that it?
Yes.
And so what is the average computing time to get, for instance,
in calibration, sorry,
to get your CP
for the PRE framework?
any of them?
So obviously, in just if it's doing cell by cell, it's just like evaluation with a pointwise estimation, right? So across, this is when you have the data. So in an absolute error residual case, when you have the data, it's a pointwise estimation. It doesn't cost that much. In evaluating gradients over here, it scales sort of linearly with the complexity of the PDE. It's not been terrible, but it's been shown to be taking slightly longer than Bayesian neural networks and whatnot. So it's I think if I can remember, in our cases looking at Navier-Stokes, it was about 200 seconds for the Bayesian sampling. Is all on GPUs, and then evaluation of the gradients was about 300. But then that's sort of the space difference that comes in. Okay. It's in the paper. Sorry, I just didn't have time to put it in.
Great, let's thank Vignesh again.